Jai Hind to all of you. Once again, I am Manish Kumar from CSE Department, Ajay Kumar Garg Engineering College. So, today I am briefing you about a topic, an important topic from the third unit, that is Bayesian learning in the series of the complex topics. Okay. So, our subject is machine learning and the topic is Bayesian learning. So, let me start the topic. Bayesian learning. So, we all know that machine learning is a multidisciplinary subject. You all know that. And in this multidisciplinary subject, here what we are trying to do, we are just teaching a machine. We are trying to give a machine a type of sense, a learning that we called a machine learning, where we have studied about the three important factors that comprises the definition of machine learning, that is T for task, E is the experience, and P is the performance measure that we have already studied about machine learning, the definition of machine learning. So, what Bayesian learning is? Actually, we know that we have studied the concept of probability, right? So, how it is used for modeling concepts. So, Bayesian probability is the notion of probability which talks about partial beliefs, okay? And Bayesian estimation, we will calculate the validity of preposition, okay? And what is the validity of preposition? Validity of a preposition is calculated based on the two things, that is the prior estimate of the probability, and second one is new relevant evidence. So, both based on this, on these two, prior estimate of the probability and the new relevant evidence, based on this the posterior Bayesian estimation is done, okay? And the key to this is an important theorem called Bayes theorem, right students? So, it deals with how to find the probability of a hypothesis, right students? So, today content will include the introduction. We will discuss about some features of Bayes learning, Bayes theorem and its concept of learning. Then we will discuss about the maximum a posterior hypothesis, that is we call it MAP, then maximum likelihood, and with the help of an example we just find out a least squared error hypothesis, and lastly we will discuss about the Bayes optimal classifier. So, this all include the Bayes learning, which is one of the important topic from the exam point of view. Okay. So, Bayesian learning methods are very much relevant in the study of machine learning for the two reasons. Okay. The first reason is that this Bayesian learning algorithm will calculate explicitly the probabilities for hypotheses, such as naive Bayes classifier is among the most practical approach that we used in learning problems. Okay. And the second reason that we provide that it provide a useful perspective for understanding many learning algorithms that do not explicitly manipulate probabilities. So, these are the two basic reasons why we use this Bayesian learning method. Okay. So, after before discussing in brief, we must know about some features of the Bayesian learning methods. So, whenever it is observed training, we observed several training examples that can base on incrementally increase or decrease the estimated probability that the hypothesis we are using is correct or not. It will provide the flexible approach, है ना? It will provide the flexible approach to learning that algorithms that completely eliminate a hypothesis. Okay, if it is found to be inconsistent with any single example, means if my hypothesis is not consistent, then we will eliminate it. Okay. Secondly, prior knowledge can also be combined with observed data to determine the final probability of hypothesis. Okay. So, in Bayesian learning, what we will do, prior knowledge is provided. So, how the prior knowledge is provided? Number one, a prior probability for each candidate hypothesis, and second, a probability distribution over observed data for each possible hypothesis. So, this Bayesian learning provides the prior knowledge by this point number one and number two. Sorry. So, Bayesian method can accommodate hypotheses that make probabilistic predictions. ठीक, and we can use new instances that can be classified by combining the predictions of multiple hypotheses weighted by their probabilities. So even in cases where Bayesian method prove computationally intractable, they can provide a standard of optimal decision making against which other practical methods can be measured. So these are the some features why we use these Bayesian learning methods, है ना? And some of the practical difficulties we face while using this Bayesian method. One practical difficulty is typically it uses the initial knowledge of many probabilities. When these probabilities are not known in advance, then we used to estimate according to the base of some background knowledge, है ना? मतलब according to the previously available data and assumptions about the form of underlying distributions. So this is the practical difficulty here we face. Second practical difficulty is that a significant computational cost is required to determine the Bayes optimal hypothesis in general case. This difficulty is the significant computational cost required to determine the Bayes optimal hypothesis in the general case. So in certain specialized situation, this computational cost can be significantly reduced. We can reduce it. Okay, so these are the two practical difficulties that we face while applying this Bayesian method. Okay, so the base is that Bayesian theorem, as I have already discussed. Okay, this so based on the posterior Bayesian estimation is done. The key to this is to use an important theorem that is called Bayes theorem. Okay, and we have all studied in our school this theorem in probability when we used to study the concept of probability. So this Bayes theorem will provide a way to calculate the probability of hypothesis, okay, based on its prior probability. Okay, the probabilities of observing various data, how we can observe the data given the hypothesis and the observed data itself. So some of the notations that we use in Bayes theorem is that P of H, that is called as prior probability of H. PD is the prior probability of D. D stands for data, observed data, है ना? PD of H is probability of observing data given a world in which H holds. H means hypothesis holds. PH of D is called the posterior probability. So a formula is there that this is the Bayes theorem. PHD PDH times PH upon P of D. So this Bayes theorem can be said as a cornerstone for this Bayes learning method, because it provides a way to calculate the posterior probability. What is posterior probability? This PH of D from the prior probability. PH is the prior probability together with PD, probability of the given data, and PD of H. Okay, so PhD increases, this PH of D increases with PH, probability of that hypothesis, and with PDH according to Bayes theorem. And this PH of D decreases as PD increases, because the more probable it is that D will be observed independent of H, the less evidence D provides in support of H. Okay, so Bayes rule is important formula from which we can link for Bayes learning. So this is an important formula. Okay, so on the basis of this Bayes theorem, on the basis of this Bayes theorem, there are several applications that we can use in the implementation. Now let us see the application of Bayes theorem. Okay, so firstly I show you an example. Let me show you an example. Yeah, consider this example, a medical diagnosis problem in which there are two alternative hypotheses. The patient has a particular form of cancer that I have denoted by cancer, and the patient does not, denoted by this negation of cancer. Okay, so this example is taken from a book Tom Mitchell. So the available data is from a particular laboratory with two possible outcomes, positive and negative. So the data is given that does patient have cancer or not. This we have to find. Okay, so probability of cancer is equal to 0.008. This data is given according to my example. Not cancer 0.992. The probability of positive having cancer 0.98, ठीक है ना. Negative probability of not having cancer, that is 1 minus 0.98, 1 minus 0.98, which comes out to be 0.02. Okay. Probability of positive having not cancer, diagnosing of not cancer, that is 0.03, and the probability of negative which are having no cancer, that is 1 minus 0.03, then it comes out to be 0.97. ठीक है. तो if we see, we can find out here, let me check what's the problem here. Yeah, so we were discussing about an example. Yeah, so using this Bayes theorem we can find out the example here na. This probability, this example is from, I am saying, from the Tom Mitchell book. The example is taken from this Tom Mitchell book. I am illustrating the example. Okay, right. So this, how we can find out this probability of having cancer with positive is equal to, how we can find it, P of plus positive having cancer times divided by P positive. ठीक है, right. And what about this probability no having not cancer, है ना, not cancer positive is equal to, how it can be find, P plus having no cancer times probability having no cancer divided by P positive. ठीक है. So we can calculate this probability. P plus of cancer is that is 0.98. Here it is. We can put it here 0.98. Okay, and probability of cancer, this is multiplied by 0.008 divided by P positive. ठीक है. So P plus, here we can find this positive having no cancer, that is 0.03 times 0.992. ठीक है, ठीक है. So now we know that the formula is, this is the formula na, Bayes theorem. So we have used this formula. So PH of D is equal to, so the goal of Bayes learning, how can Bayes theorem we apply to find a hypothesis on machine learning? Now the problem is that, so the goal of Bayes learning, how can Bayes theorem we apply to find a hypothesis in machine learning? So based on Bayes theorem we can find out the most likely hypothesis. ठीक है. So based on Bayes theorem we can find out the most likely hypothesis, which is called the maximum posterior hypothesis. This, now we are going to discuss about a maximum posterior hypothesis, MAP. ठीक है. So MAP hypothesis is given by that value of H for which probability H, for which the probability H given data is maximized. So H map will be given equal to argmax H, my hypothesis belongs to this H, hypothesis space P H of D. So this Bayes theorem to calculate the posterior probability of each candidate hypothesis is H map, is a map hypothesis which is provided using this. ठीक है. तो we know that from the Bayes theorem we can put the value sorry, we can put the value of this PhD. We have put it here, P D, my data of H, times PH divided by PD, and we can neglect this PD term. We can drop this because it is a constant. It is a constant independent of H. Okay. So now we will see an example of how in finding the least squared line we can apply the Bayes theorem to find out the most likely hypothesis. We will see an example. Okay, I just show you an example ki how we will find the least squared line. We can apply the Bayes theorem to find out the most likely hypothesis. We will see the example after this. Okay, so in some cases it is assumed that every hypothesis in H is equally probable a priori. Ph of I is equal to Phj for all Hi and Hj in H in my hypothesis space. So this equation can be simplified as this. Okay, so what is this? P d of H is often called this is called the likelihood of the data D given H, and any hypothesis that maximizes PDH is called the maximum likelihood. That is called maximum likelihood. So this is important, maximum likelihood. Okay, so this is the maximum likelihood, MHML. Okay, students. Okay, this is the maximum likelihood. Maximum likelihood. ठीक. So this we have discussed already. So Bayes theorem and concept learning. So how this concept of learning is related to this Bayes theorem? So what is the relationship between this Bayes theorem and the problem of concept learning? Since Bayes theorem provides a principled way to calculate the posterior probability of each hypothesis given the training data, and can use it as the basis for a straightforward learning algorithm that will calculate the probability for each possible hypothesis, then outputs the most probable. It will always output the most probable hypothesis. Okay, so we will learn this concept as a brute force based concept learning. So we can design a straightforward concept learning algorithm to output the maximum posterior hypothesis. So to output this maximum posterior hypothesis, which is based on Bayes theorem, that can be represented as follows, which we call it brute force map learning algorithm. Okay, number one, so for each hypothesis H in H, means this H which will belong to H, calculate the posterior probability. How it is calculated? From our formula of Bayes theorem it is calculated. Okay. Number two, it will output the hypothesis H map, है ना, maximum a posterior with the highest posterior probability. And what is the formula of that highest posterior probability? Arg of max H belongs to H, PhD. Okay. So this is the learning algorithm that can be related to that concept of learning. Okay. So in order to specify a learning problem for a brute force map learning algorithm, we must specify the values which are used for PH and P of DH. Okay. So let us choose this PH and PDH to be consistent with the following assumptions. So we will consider that the training data, our training data will not consist any noise. Okay. The target concept C is contained in the hypothesis. We will consider that target concept is already included in that hypothesis space H, and we have no priori reason to believe that any hypothesis is more probable than any other. Okay. There is no other reason that this priori is a reason where that I have already discussed, that it will consist of all the legal moves. Out of those legal moves, one best move will come out. So that reason is called as priori reason. Okay. So we have no a priori reason to believe that any hypothesis is more probable than any other. Okay. No prior reason is there. Okay. Our training data is noise free, number one, and this target concept C is contained in our hypothesis space. So considering this, we have chosen PH and PDH to be consistent. Okay. So what value should we specify for PH? So for specifying this value, we have already told that no prior knowledge that one hypothesis is more likely than another. It is reasonable to assign the same prior probability to every hypothesis H in H. So we have assumed the target concept is contained in H. This is my second point. This is my first point that I have already briefed here. Na? So considering this, assuming this target concept, we require that these prior probabilities sum to 1. Okay, so it is represented like PH is equal to 1 upon H for all H belongs to capital H, my hypothesis space. Okay, so what choice shall we make for PDH? This is for PH. Number one, this is for PH, and number two, second choice is for PD of H. So this is the it is the probability of observing the target value. Okay, so we will consider the data D, D1, D2, D3 up to Dm for any fixed instances. For example, number of instances from x1 to xm in the given world in which hypothesis H holds. We have assumed that these are the instances and these are the target values. Okay, and since we have assumed noise free training data, the probability of observing classification that data Di given H is just 1, है ना, sum is equal to 1. So if Di is equal to Hxi, if Di is equal to Hxi and 0 if Di is not equal to Hxi. So we can have a choice that the value of this probability of our data with H is equal to 1, it is equal to 1 if Di is equal to Hxi for all Di belongs to this D, otherwise the value of P Dh is equal to 0. Okay, so this we have find these two values, P of H and secondly P of Dh. Okay, now given these choices for PH and PDH, we now have a fully defined problem for this brute force map learning algorithm, है ना. So in our first step we have determined the probability of PhD. So we have H is inconsistent with training data D. So if it is inconsistent, we put it here 0. So it result into 0, है ना, number 1. Secondly, if H is consistent with the training data D, then we put, if it is consistent, then we will put here is equal to 1. Now, from where this pH comes, we have already find out here. This pH is equal to 1 upon H that we have considered, है ना, on the basis of our these training data is noise free and number 2 target concept C is contained in hypothesis H, है ना. We are come up with this probability of H 1 upon H. So we have put it here and solving this Vs version space, we will get this value. Okay, so this is the brute force map learning algorithm. Okay, so to summarize what we have derived, this Bayes theorem implies that the posterior probability under our assumed pH and PDH is defined as is equal to 1 upon VHD if it is consistent. If it is not consistent, then it comes out to be 0. Okay, where what is this Vs HD? It is the number of hypotheses from H consistent with D. Okay, that we have briefed in unit number 1, that is called as version space. Okay, the hypothesis H, hypothesis space, and D stands for our data. Okay, so the evaluation of this probability, how the evaluation of the probabilities is associated with hypothesis. So see this diagram, figure A. Same these figures are taken from the same book, Tom Mitchell, for your reference. This figure A will show me all the hypotheses have the same probability. ठीक है ना? This is the pH, this hypothesis having the same probability. Okay. Figure number B and C. According to that training data, the posterior probability for inconsistent hypothesis becomes 0, while the total probability summing to 1 is shared equally among the remaining consistent hypothesis. Okay, so these are the two figures A and B. Okay, here it is showing the same probability, but here the probability is not same, it is varying. Okay, so map hypothesis and consistent learner, what does it mean? It means that a learning algorithm is a consistent learner if it outputs a hypothesis that commits 0 error. If there is no error, okay, over any training example. So every consistent learner outputs a map hypothesis, maximum a posterior hypothesis, this map hypothesis. If we assume a uniform prior probability distribution over H, how it is assumed? Uniform distribution, P of Hi is equal to P of Sj for all ij and deterministic, assuming noise free training data. If training data is noise free, then the probability of this is equal to 1 if D and H are consistent, otherwise it will be 0. Okay, so we have seen several examples in previous units like candidate elimination algorithm, like find S algorithm, and that will output a consistent hypothesis. It will output a map hypothesis under the probability distribution PH and PDH defined above. Okay, so are there other probability distributions for PH and PDH under which find as output map hypothesis. What is the answer of this? Are there any other probability distribution for PH and PDH under which find S outputs map hypothesis? Yes, there are. Yes, the answer is yes. Because find S outputs a maximally specific hypothesis from the virgin space. Its output hypothesis will be a map hypothesis relative to any prior probability distribution that favors more specific hypothesis. Okay? So this is the reason. Because find S outputs a maximally specific hypothesis. We have shown there that how we can this from specific to general, a general to specific hypothesis for a given virgin space, how we find the output for the particular hypothesis. So the answer is yes. Okay. So Bayesian framework is a way to characterize the behavior of learning algorithms. So it is necessary. So by identifying the probability distribution PH and PDH under which the output is optimal hypothesis, implicit assumptions of the algorithm can be characterized. That we have already studied inductive. What is inductive bias? So inductive inference is modeled by an equivalent probabilistic reasoning system based on Bayes theorem. So that reasoning system is generated on the basis of that Bayes theorem, that system. Okay, that inductive inference that is modeled on this Bayes theorem. Okay. So now let us come with the example. Now I just want to show you. Now we will see an example of how in finding the least squared line we can apply the Bayes theorem to find out the most likely hypothesis. Okay. So suppose we have to learn a real valued function. Now I just show you with the help of the example. So for example, that we are considering a problem of learning a continuous valued target function. Okay, such as for example, any example we can take. We can take an example of neural network learning, number one. We can take the example of linear regression. Okay. Also we can take an example of any polynomial curve fitting. Okay, any of the example. So I just try to show you an example of this linear regression. Okay. So a straightforward Bayesian analysis will show that under certain assumptions, any learning algorithm that minimizes the squared error between the output hypothesis predictions and the training data will output a maximum likelihood. Okay. So our aim is to just find out the output that according to the given training data, the output is a maximum likelihood hypothesis. This is our aim. Okay. So suppose we have to learn a real valued function. Okay. Learn a real valued function. Okay. So we have talked about linear regression which can be used to learn a real valued function. And suppose the data is generated in following fashion. Like for example, we have considered data is generated like this. Here I am assuming this is my x, this is my d, okay, and this is my output function fx, okay, and the data is lying here like this, for example. Okay. So and suppose the data is function f, है ना, and individual data are generated. So data is given as xi comma di, ठीक है, are the individual data points, and di that is defined on the basis of a function f xi plus epsilon. Okay, epsilon I. This epsilon I is the error. Okay, that we this error epsilon I is the error. Okay, this epsilon I is the error. We assume that this error follows a normal distribution. This error follows a normal distribution. What does this mean? Normal distribution. Normal distribution means which is having a mean. This mean is equal to 0 and that standard deviation is sigma. Okay, mean is equal to 0, mean, okay, and this standard deviation is 0. So this error will follow a normal distribution. Okay, so di is coming from, so this di is coming from normal distribution, है ना? Di is coming from normal distribution, okay, such that basis on the function of fxi, okay, having this standard deviation sigma 0, ठीक है, whose mean is fxi, whose mean is fxi, mean is fxi, है ना, and error is given by sigma square, error is given by sigma square, okay, where sigma square is variance corresponding to this error term. So this is how data is generated, and let us assume that epsilon I is, let us assume that this epsilon I is independent. This is independent, okay, this is independent, that is it is independently generated for the individual instances, where epsilon I are independent for different instances, ठीक है, and it is a Gaussian with 0 mean and variance sigma square. So we can say that data is generated as normal distribution fxi comma sigma square, ठीक है. So now we have to find the function. Now we have to find the function. So let us say we use, let us say we use maximum likelihood, ठीक है, hypothesis. Now let us say we use maximum likelihood hypothesis. So this is used as h of ml that we have already derived, maximum likelihood probability, that is equal to arg of max, h belongs to our this capital H, ठीक है, और h है ना, that is defined as p my data of dh. This is the maximum likelihood hypothesis, ठीक है. So this is derived like this. So for this function, this h, we can define it as a product 1 for all hypotheses, 1 for all instances, I is equal to 1 to m, defined as 1 upon under root 2 pi sigma square, ठीक है, e raised to the power minus 2 d minus x का whole square upon sigma, okay. See, yeah, this है ना. So let me show you in the PPT. Yeah, this I have showed you how this equation comes. This is epsilon I, ठीक है. So output is a maximum likelihood hypothesis, okay. See, this is a function that I have shown you, for which we have finding. This is a training example. I assumed to have normal distribution, noise epsilon I with 0 mean, and to the true target value fxi, ठीक है, the same that I have shown you here. Yeah, here, okay. So the probability, this is a normal probability distribution, because I have told you that this, we have considering the error is a, it is generating with this distribution, normal distribution, है ना. So a normal distribution is smooth bell-shaped distribution that can be completely characterized by the mean and its standard deviation sigma. So what is the equation of this? So the same equation I have used here, okay. So which is a bell-shaped. So this I have refer for your reference why from where this equation is coming, which tells this Gaussian distribution, okay. So a normal distribution fully determined by 2 parameters in this formula, ठीक है, variance x, sigma square, standard deviation, okay. This is a formula for maximum likelihood that is derived. Okay. So this is exactly the least squared criteria. This is exactly the least squared criteria. Okay. So this is a Bayesian explanation to why we would choose a sum of square error to minimize in order to find out the linear regression. Okay. So how we can show it? See, this is, so for solving this we have taken the log ln. So this term will be considered as constant. So we have neglected this term. So only this remains. See, so we can write this. Here it is written as arg max h. We have sigma. We have converted into this, taking the log of both sides. We have transformed this into this. I have considered this term as a constant. So we can neglect this term. It is a constant. So we can return this equation as arg of minimum can be written like this. So maximizing this negative term is equivalent to minimizing the corresponding positive term. So we can write like this also. This is the maximum likelihood. Okay, students. So if we are given the training data, from the training data we learn H map. Okay. Now we will study about the Bayesian optimal classifier. So what is the Bayesian optimal classifier? I just want to explain you about after this. So keeping in mind this, we are using this maximum likelihood is one of that, minimizes the sum of the squared error. So this is the reason why we are using the this least mean squared. This this equation is minimizing the error. So this is the just illustration of the concept of Bayesian learning. Okay, that I have shown you. So Bayes optimal classifier. Now next we will study about Bayes optimal classifier. So if we are given the training data, from the training data we learn H map. H map is the most probable hypothesis. Okay. So but H map is not the most optimal classification. Okay. For example, firstly I just want to show you, for example, I have taken the three H1, H2, H3. These are the three candidate hypotheses. These are the three candidate hypotheses. Okay, belonging to the hypothesis space. Three candidate hypotheses belong to the hypothesis space. And suppose probability of H1 with D given data is equal to 0.4. Probability of H2 with the given data is given as 0.3, and probability of H3 with given data is also 0.3. So which one is the map classifier? H1. Okay, H1 is the map because it has maximum posterior probability. This is given. Okay. Suppose we are given a new data. Now suppose we are given a new data. Okay. And suppose in new data we have given this, for example, H1 positive is equal to plus H1 of x is equal to plus H2 of x is equal to negative, H3 of x is equal to also negative. Now in this case the most probable classification would be actually negative. It will actually negative. You will say it is positive, but actually it is negative. Why it is negative? Because the sum of the probabilities of these two hypotheses, it comes out to be 0.6 na. So we can say that the most probable classification would be negative. Okay, because the sum of the probabilities of these two hypotheses is 0.6, which is larger than the probability of the hypothesis, this 0.4. So 0.6 is greater than 0.4. This is the most probably specific. So what we have is, we have what we call the Bayes optimal classification. We call it a Bayes optimal classification. Okay, so it is given by this arg. This is given by arg max Vj belongs to V sigma, my H I belongs to my hypothesis H, this P Vj divided by Hi times Phi by D. So this is the Bayes optimal classifier. So Bayes optimal classifier will output the class for a classification. Okay. So Bayes optimal classifier will output the class for a classification problem, for which if you take the summation over the entire hypothesis space of probability Vj given Hi times probability Hi given data. Okay. So in order to find out the Bayes optimal classifier, we have to, for that test instances, we have to apply all the possible hypotheses on that test instances in order to find out the Bayes optimal classification. Okay. So it is optimal because no classifier using this same hypothesis space and same prior knowledge can outperform this on the average. Okay. So we can see typically the size of hypothesis space is huge. What we have seen here in this Bayes optimal classifier, the size of hypothesis space is very huge. So it is not possible to apply the Bayes optimal classifier. So we have to use some approximation for this. So for approximation, we will use that Gibbs sampling. So what is that Gibbs sampling? Gibbs sampling is just to choose a. So this cannot be practically implementable. We cannot implement practically. So for practically implementing, we use an approximation, and that approximation is called as Gibbs sampling. So in this Gibbs sampling, we will choose a hypothesis randomly according to pH of D. है ना? तो we will use it to classify the new instances. Okay. So that's all for today. So this is the important. So I think you should understand the concept of this Bayes learning, that is based on this important concept Bayes theorem, then that map, then maximum posterior probability, then Bayes optimal classifier. Okay, students. So thank you for today.